So it's my pleasure to introduce Boris Adamczewski, and we'll speak about algebraic independence of G-functions via reduction modulo prime.
Okay, so thank you very much for the invitation. I'm going to speak about algebraic independence. Independence of the Siegel G-functions. Reduction.
Would you bring the chalk?
Break it. Yes. This is already there. Could be better. Is it better? No?
No, you bring that one?
Yeah, but they are quite small, so I try to. And this is joint work with Jason Bell and from Waterloo University and Eric Delaygue from Lyon University. And there are also ongoing works based on this kind of same idea that includes Siegel G, which is also a colleague in Lyon. I don't think I will really touch this part. So the idea is to describe a new method to prove algebraic independence of G functions. I'm going to introduce, but not using the classical approach. So I first remind you the definition of G functions. So they were introduced by Siegel in 1929, and so the G function is a power series from with algebraic coefficients, and that satisfy so f is a G function if the following three conditions are satisfied. So the first one is that f satisfies a linear differential equation with polynomial coefficients. So that satisfies a linear differential equation. And the second and third condition, they are just saying that the arithmetic growth of the coefficient is not too big, so it is under control. So we have that there exists a positive number C such that the modulus of the Galois conjugate of AN are at most C to the n, and there exists a sequence of natural number Dn such that Dn is at most C to the n, and Dn An is an algebraic integer for all m between 0 and n. We can multiply it by this number Dn, and all the first m coefficient become an algebraic integer. So these two could be rephrased by saying that the projective 8 of the first n coefficient is not too big. Okay.
Could you read 2 and 3 again? Could you just read?
So the modulus of the Galois conjugates of the coefficient am. So they are at most equal to c to the n.
What is modulus?
Just the
Absolute
absolute value.
Absolute value.
Yeah.
Absolute value.
And there is this sequence of integer of natural number dn, which also are at most c to the n. So that if you multiply the first n coefficient, any of the first n coefficient am, by this dn, they become an algebraic integer. Okay, so this.
This is dn am, right?
Yeah.
Okay.
dn, so dn is at most c, and if you multiply any of the
Smaller ones.
am with a smaller one, it becomes algebraic integer. Okay, so this is the definition suggested by Siegel.
And then this has to hold for all n.
Yeah.
Okay.
Yeah.
Yeah.
Okay. It's true for all. These two are, of course, need to be true for satisfy for all.
So what is an example?
There are a lot of them, and I'm going to explain a bit also the philosophy of that. So, among the examples, so you have the algebraic power series. Algebraic power series. Maybe I will define later the diagonals of rational or algebraic functions is the same.
What's algebraic power series?
So power series, which are algebraic over the base field of
okay.
rational functions. So there are algebraic functions that we also have that they are power series. So you don't want to have all the function. So diagonal of rational power series. The series like 1 to 6, some of and you can have all the hypergeometric series f plus 1 fr. So I'm going to give the definition here. So you choose parameter alpha 1 to alpha r plus 1 and beta 1 up to beta r. So this is defined to be the sum over n of the alpha 1 n alpha r plus 1 n divided by the beta 1 n beta r n. So if alpha I and beta I are rational numbers, we avoid negative integer for the beta 1 for the series to be well defined. So there are again examples of G-functions.
There is, okay, now I see, because you were hiding here.
Yeah.
There is a C was behind you. No. I was trying to read the definition again.
Okay.
I didn't see part of it. You were
And another famous example is a Algebraic generating series. So if you consider the sum over n, the sum over nk 0 to n of the nk square n plus k square z to the n. So this number, the an, are known as the Algebraic numbers, so they appears in the proof of irrationality of zeta of 3 by Algebraic. So this generating series, for instance, is also an example of a G-function. Okay, we have already plenty of them.
What is so special of this versus just any power series with rational coefficients?
Okay, so the idea is that
What's number one is my
Number 2 is right.
no, number 2 is okay.
No,
The
no, no,
coefficients
you
are
need
just-
to-
You
So
have
you mean
arbitrary, then could
Yeah,
go
so-
bigger than that.
oh.
You have that
Number two is like converging, so you need that they converge.
Okay, convergent power
But,
series.
but when you have this, also the thing for the Galois conjugate and the last thing, so I'm going to explain the picture. So it really defines much more interesting classes just if you consider power series, say, because you can also work with it. So I describe the situation. The situation is in analogy with what happened with numbers.
You're giving some particular examples.
Yeah.
In all cases, the coefficients belong to Q, right?
Yes.
So what if you just take an arbitrary convergent power series with coefficients in Q?
You need
Number one.
and satisfying number one.
So, satisfy
Yeah.
number one. So any convergent power series that
Sure.
satisfies
Yeah.
one is good.
Yeah, exactly.
That's right.
And this is basically, I mean, because Siegel, he was in the number theory, so he introduced the G function at the same time he introduced the E function, and he has a method to prove algebraic independence for values of E functions. And all this machinery work over number field. So when I say that the coefficients are algebraic numbers because of one, they are actually in a given number field. So all definitions are given in number field because sometimes, I mean, it just all the theory works in this more general framework. But concretely, all example people are interested in and are looking at are power series with rational coefficients. Okay, so but the definition is given over number field. Because what you try to do is to mimic this. So you get, if you consider number, so we have the rationals inside the algebraic numbers, and maybe you can consider the complex numbers, and the point is always the same. So here you have something countable, you understand quite well, but many numbers are missing, like PR, log 2, many interesting numbers are missing, and this is really too big. So people have tried to imagine what could be inside, and there are of course several possibilities. One attempted to look at the ring of periods, so which are defined as integrals of algebraic functions over a semi-algebraic domain. So it means that you just allow integration, and then starting from algebraic numbers, algebraic functions and algebraic domain. So what you get is almost all interesting number, but still you have something which is countable, and the element in P can be described with a finite amount of information. Okay, so this is something people have tried to mimic, and already Hilbert, he observed that you have the same kind of things here. You can consider instead of Q the rational functions, instead the algebraic functions, and maybe here, so I could independ. So either I can consider power series here, in which case I have to consider rational power series to obtain the right inclusion. Okay, maybe power series, rational power series inside algebraic, and then there's the same thing. So the question is, what could you put here inside? And there are several choices. Maybe you can choose a holonomic function, just saying satisfying, or maybe we start with C here. So you could consider maybe the holonomic or differentially algebraic power series, but also the G function. So this is a third possibility. And again, if instead of looking at C as a base field, you start with Q bar, then the point is that whatever the choice here, it becomes countable, and elements can be described by a finite amount of information. The point is that if you choose one of these two, there are good connections, say, with combinatories and also arithmetics, but they are a bit too big, so to make a strong connection with arithmetic geometry. What is expected is that these G-functions, they are always connected to some geometric situation. This is the so-called Bombier-Dwork conjecture. Let's say that when you have a G-functions, you consider the minimal operator associated with this function, so because it satisfies a linear difference equation. So this operator should come from geometry, which makes a connection with some algebraic variety. Okay, so if you want this connection, you have to focus on this G function. Okay.
What kind of operation is are G functions closed?
The G functions, so first they form a ring. It's closed under derivative, Hadamard product.
Integration?
Not integration. And that's it. For the, I mean, maybe there are others, but the one can come back to me. Okay, so now what I want to do is what? Yeah, is to explain. So the problem we have. So as I say, we would like to find tools for proving. So here, the main question is understanding the algebraic relation between periods, and in particular prove transcendence and algebraic independence among several of them. But most of questions are far open. We have only really few tools to find irrationality, transcendence, or algebraic independence results for periods. The idea that if when you are at the level of power series and functions, you have more tools, like the derivative, that you can use, and the problem is easier. Okay? But still, it's easier, but not always easy. So the question is that what can you do if I give you F1 to Fn some G functions? And the question is find tools for proving algebraic independence of such functions.
And by
They are not always algebraically independent, but I mean, in many cases, I can give you some example like this and ask the question. So, and the question is what kind of tool we can use to prove this algebraic independence?
by C they're given, would they be given by the differential equation and initial conditions?
Yeah, yes. I mean, the problem is quite vague. So you can imagine, just I give you an explicit example given by a formula like this, like hypergeometric series, and ask you, can you prove that they are algebraically independent? I'm going to give an example in a minute. Of course, also you could ask for a general algorithm to decide this or something like that. So there are several kinds of questions you may imagine. So what I want to say is that the very first idea you can have is to use a differential Galois theory, because by definition, all these functions satisfy a linear differential equation. But the point is different. Yeah, I just picked some of them. But the point is that imagine you have few of them, so this one satisfies an equation of order 2, say, and the second one an equation of order 3, and so on. So if I want to use differential Galois theory, I have to find a differential system with all these functions. So maybe the size of the system will be the sum of the, at most, but sometimes smaller, but say it will have the sum of the size of each system, so it may become quite big. And then I can try to understand the differential Galois group. There are algorithms in principle for that, but as far as I understand, if the order becomes quite big, it's not clear at all that you will run this algorithm. Also, even it's not completely clear if you know the Galois group, in theory you know all the algebraic relation. But there are also some change of variables when you want to express things with torsor, so which it's not completely clear if you give me the Galois group, how to know that for these special functions,
I'm not sure
what
you know
are
all
the
the
relations. Yeah?
I'm not sure that you know all the relations.
No, but
I think you know like kind of what the shape is,
yes, exactly.
but not exactly what the
Yes,
relations are.
so that's the point. So maybe on some, I will give you later one example, but on some examples, so of course this will work, but not always, and even if the theory is well developed, sometimes you are just stuck with your examples. Okay? So and the idea is that to show you that sometimes there is just a small trick, rather easy, that will give you the answer very easily. So that's why I'm going to describe.
Excuse me.
So it's a different approach.
Is there an algorithm, if I give you a function,
Yeah.
that you can tell it is a G function?
If you give me, no. I mean, if you give me just a differential equation, and I have to check just by the differential equation and initial condition, if it is a G function.
Well, actually, if I just give you a function, how can you tell it is a G function or not?
How do you give me the function?
Well, by some expression.
So if it's given by the series, so sometimes, so for instance, for this hypergeometric
Let's say
series,
it's in terms of exponential and log and whatever.
I can just try to check the three conditions. I mean,
Well, if it is exponential log, I guess
yeah,
it is.
when you have some exponentials, so most of the times you know that they are E functions, they are very different from G functions. So the G functions, they have a finite radius of convergence.
Yeah, what?
Finite radius of convergence.
Finite? Why?
Yeah,
Why finite?
because of the condition on the height. So the G functions, they all have modulus. They have modulus at most C to the n.
Ah,
The radius of convergence is finite. Unless they are polynomial.
Another condition. No. So maybe. Wait. It is the other one that. No. What's up with the exponential function? Why does it not satisfy the?
Because the exponential function, so you get this n factorial here.
Yes. What's wrong with n factorial?
So it's just that
What was the condition?
the size, I mean, to become an integer, the third. So
Third
it's
condition.
because of the 8, because it's really small in the modulus, but the 8 is really large because of the n factorial. So if you want to make this coefficient, an is 1 over n factorial.
Yeah.
So if you want to find this dn to make it an algebraic integer, so the
Yeah,
dn
the function will be n
has to be n factorial. So it's
what's wrong with
so
that?
it just it should be smaller than
right,
dn.
we should, okay.
The condition.
Yeah, the dn
Our
is
C chosen uniformly for the whole thing.
Right.
Yeah.
Okay.
Yes. So that's exactly.
You can't go too fast.
Yeah. No, you can't go too
The
fast.
denominator can't go fast.
No. You can. But okay. So sometimes it may be, depending on the expression, a bit tricky to check that it is a J function.
Right.
But you can. So for instance, proving that.
Actually, I mean,
Proving that those ones, this R plus 1 FR with rational parameters are G function, it's probably more or less like an exercise, but I don't know if it's really trivial. So sometimes you need some.
You probably can see it rather than using an algorithm.
Yeah. Most of the time we just.
But if I'm just giving a sequence of rational numbers, as I said, then in order to check that, to find that C, right?
Yeah.
You have to go through, is there a way to find that C? Or show that it doesn't
That's
exist?
always the same.
Or show that it doesn't exist?
Yeah. So it depends on what is the formula you can give to me. So if you expect a general answer, it should mean that is there.
Suppose the answer is by some difference equation.
I don't think there is general. I mean, even if you give me a differential equation, so I will have a polynomial recursion for the coefficient.
Okay.
I don't think there is an algorithm to know in advance whether it is a J function.
Okay.
Okay, so it's more, I don't know. We have on one side a collection of examples. We can check it by hand.
So the f and here are given, I mean, in the problem here. The f n's are given what? By means of the
what I have in
series
mind is,
solution to differential
yeah,
equation.
I'm going to give you example of series, and the idea is sometimes we seems to be either a difficult exercise or lengthy exercise to prove it by differential Galois theory. For this example, I'm going to show what we can do. But for this, still there is a general framework I want to give you. So maybe the best is to start with the example that motivates this work, because it's really simple to understand. So we pick R is equal to 2, a natural number. And the series we are interested in are FR of Z, which are defined to be the sum of the central binomial coefficient to the power R, Z to the n. Okay, so we have integer coefficient power series, very basic and simple. Those are G-functions. So they are, it's not hard to check that they satisfy linear differential equation. So they are close to be hypergeometric series. And so of course here's the coefficient in Z. And those kind of series, because they have integer coefficients, they are counting things. For instance, if R equal 2, so if you consider the lattice work on the plane, where you can go in each direction, north, south, east, and west, if you count the lattice work that start from the origin and come back to the origin, so the number of such a work is related to this 2nn square. So this is a kind of generating series people in combinatorics can have into their hands. And in 1980, so Stanley asked the question, so for R equal 1, we get an algebraic series. So it's just a square root of 1 minus 4z. But when R is larger than 1, so Stanley conjectured that FR is transcendental. It's a transcendental function. And he observed that this is true for R is even. So OK for R is even. And I'm going to explain in a minute how he checks this. So the strategy of Stanley was to use Stirling formula to get the asymptotic of coefficients, and to show that these asymptotics cannot be not fit with the asymptotic of an algebraic series, right? And this has been, so the question was finally just solved. I mean, it's more or less a remark, but already you need some tools by flageolet with the same techniques for all R. So he answers Stanley question, and the idea is that the 2nn R, so the asymptotic is like this, so it's 2 to the 2n plus 1 R divided by 2 pi n R over 2. Okay? And what is known, so this is just using Stirling formula. And on the other hand, what is known is that if series, so if f of z, sum of a n, z n is algebraic, alpha to the n to the s divided by gamma of s plus 1 sum of ci wi plus little o of n to the s alpha n. So some correcting term, and here you have, so this sum is finite. Finite sum here, and this number alpha has to be algebraic. So this is this S belong to Q minus the negative integers, and the WI, they are also algebraic. Okay, Ci and WI are algebraic. So when you have this description, so what you see here is that we have a similar expression with S is equal to minus R over 2. So when R is even, we have a negative integer, so which is not allowed for this kind of expansion. So that's why Stanley said. But when R is odd, so we get something like S should be minus n plus 1 half. Okay, and so the alpha is 2 to this something, so it's still it's well algebraic. The S is okay, so you have to see this is algebraic and this is gamma of S plus 1, and the gamma of minus n plus 1 half belongs to the field Q of square root of pi. And if you compare with this, it doesn't fit anymore. So it means if you use the transcendence of pi, then you can show that because of this coefficient, that one cannot be the asymptotic of an algebraic series. So it's purely analytic, but already choose the transcendence of pi to get the answer. Okay. And so this gives us a transcendence of all these functions. And after the work of Bernoulli and Stanley with this asymptotic, so there are two other ways for proving the transcendence. The second approach, so let's call this 1. So the 2 is 1987, and this is due to Sharif and Woodcock. And what they use this fact. So if you consider FR mod P, which means the sum of the 2 and R mod P, where P is a prime number, so you reduce the series just coefficient by coefficient. So to prove that this is algebraic over P of Z. Okay. So if you have an algebraic series, it satisfies an algebraic equation. If you reduce modulo prime, you will get something algebraic. But the degree remains the same for almost every prime. So, and they prove that this thing is algebraic, but the degree is not bounded. So plus some work to prove that the degree is not uniformly bounded in P. So you can reduce for each prime it's algebraic, but the degree when P moves cannot be uniformly bounded, so this proves that the function is algebraic, is transformable. Okay, so this is the second proof, which is more or less purely algebraic. Because to prove that this is not bounded, they use some kind of analytic number theory, so it's not completely algebraic. And the third way you have to get with the transcendence is to see that this FR, if you consider FR of just, you can write this as a hypergeometric series. So it is a R plus 1 FR, I gave the definition a few minutes ago, of 1/2 R plus 1 times, and N R times. And because this is a hypergeometric series of types R plus 1 FR, if it was algebraic, so the corresponding differential algebraic group would be finite, but a finite differential group of hypergeometric series of that type have been characterized by Bakers and Heckman. So you can use Bakers and Heckman to check that Bakers-Heckman interlacing criterion to check that this is transcendental. But already here you need to know things about this work, because this is hypergeometric and you need all the work of Bakers and Heckman. So we show you already for transcendence, so this would be the classical approach by differential Galois theory. And we have these two other approaches, one by asymptotics and the second one by reduction mode P. The idea is that if you want to go further and look at the algebraic independence of this power series, you can still use differential Galois theory. So the question now, and actually this is a theorem, so I mean, this is a theorem we prove with Bell and Delaygue, but it's just more or less just an example of what we are doing. We prove that all the function fr r is equal to p are algebraically independent. Okay. So if you want to go from transcendence to algebraic independence, so this three approach is still available. But I discussed with Bakers, and it's already a lengthy exercise in differential Galois theory, because you have to put all these hypergeometric series F1 to FR together. And so now you have your knowledge on the hypergeometric differential group, and show that things cannot be compatible. And finally, you can prove that they are algebraically independent, but you have to do some work on algebraic groups, knowledge on algebraic groups. The point is that because you are interested in algebraic independence, only use asymptotic is never enough, because you have sums and products of things. So usually, just looking at asymptotics can just say nothing. And our idea is that using this approach, so basically the approach I want to describe is 2 plus 1. So we will use this things mode P, so that at the end we could use the asymptotic techniques in a very easy way. So instead of 3, we want to replace 3 by 1 plus 2. Okay? So to explain this, the first question you may have is, why these series are algebraic mode P? So it's a bit surprising, I don't know for you, but first time I saw that, because I want to describe a method to prove algebraic independence for series which are algebraic mode P. Okay? Maybe just an accident, and you get just by chance that these series are algebraic mode P, but the first question is why, and is this relevant in some sense? So why answer algebraic mode P, or this kind of function? And for this, there are two ways of looking at this question. So the first, I call it from the bottom. So, which means we can just check it, and it comes from an old theorem by Edouard Lucas. So it's called Lucas theorem. It follows from Lucas theorem. It's just a little bit more general. That if you look at the binomial coefficients, so if you consider the two, it's a what? 2 and p is j and j. So instead of the 2 and n, you look at the extraction between this arithmetic progression and p plus j. So this is congruent to the 2 and n to j. And here j is between 0 and 2. We fix a prime number, and Lucas theorem is just a bit more general than this, but it gives you this congruence. Okay, it's a very old result, easy to prove. And if you look at the effect on this on power series, so it gives you that, of course, this remains true if you put a r here. And what you get is that the fr of z, you can write it as a sum from j equals 0 to p minus 1 of the 2j r z j. So this is just a polynomial of degree p minus 1 times fr of z to the p. We just have split along arithmetic progression. And of course, this f of zp, so this is true mod p using this congruence. And this is fr of z of zp, this is just fr of z to zp. And this is just an algebraic equation for f. Okay? But the idea is that, for instance, when you look at the Apéry sequences of hypergeometric series, so in a sense they inherit this basic, you will have sum of product of binomials, sometimes in tricky forms, but most of them inherit this kind of congruences. So you can just work from the bottom, starting from these simple examples, and show that more and more complicated examples still satisfy this kind of equation. But you can also look at this from the top, and if you don't like this explanation, we also have the following one. So it's on the top. So by this I mean that if you start with G-functions, which is our target, so as I mentioned, there is a conjecture by Bombieri and Dwork. So this is a conjecture, I should say conjecture, that it comes from geometry. So it should comes from geometry. So there are factor of Picard-Fuchs equation comes from geometry. And when you have differential equation that comes from geometry, so there are results by Katz saying that this kind of equation they can be handled with a strong Frobenius structure for almost every prime number. So you have Frobenius structure for almost every prime. Okay, and then for instance, Vargas, my student Vargas Montoya, proves that if you can reduce mod p, the reduction will be algebraic. So algebraic below prime ideals. So when you have G-functions, so they're supposed to be defined over a number field. So reduction means reduction modulo prime ideals. So So by this conjecture, there should be a geometric context, and then you get this Frobenius structure for almost every prime. And then if you can reduce, the reduction should be algebraic. And if you have an algebraic, so here's the reduction, even if you are over a number field, you reduce modulo prime ideas, you get a finite field. So what you get is this algebraicity mod P should look like an equation, and you can find an Boris equation, which is an equation of the form A0 f of z plus A1 of z to the p plus AD of z f of z p to the d is equal to 0. Okay, so once you are algebraic mod P, you always get an equation of this form. Again, or maybe you should take a power of P depending on if you are not over Fp but of if you are an exertion of Fp, to get an equation where say the P are inside. And this, I want to think about that as a difference equation associated with the Frobenius. So for me, this algebraicity, I just think about it as a difference equation. Say Frobenius. Difference equation. Okay, so which means associated with the endomorphism z give to zp, right? So the general picture is that each time you take a G-functions, but it should come from geometry, you get this Frobenius structure. So if you can reduce mod P, they are algebraic, so they satisfy this kind of difference equation associated with the Frobenius. So which show you that when you start with this framework of G-function, you not only have one differential equation, but also plenty of difference equation mod P. And this is what we are going to use. Just one thing is that here there is a warning. So I say if you can reduce. So of course, if you choose the logarithm of 1 plus z, you cannot reduce the coefficient mod P. So just the method tell you nothing. Okay, we want to here to stick with coefficient that can be reduced mod P for at least infinitely many prime ideas, right? So these are the bad guys. Yeah.
And also, does that mean you believe the conjecture?
Sorry?
Does it mean you believe the conjecture?
Yeah, I believe the conjecture. I mean, everybody seems to believe this conjecture. And this conjecture is fascinating. So, I mean, we know that the guy that comes from geometry are G-functions, right. So this part is known. And what is really fascinating is that this very naive definition of Siegel should capture exactly correspond to this geometric setting. So that's why people are quite excited by this conjecture. I mean, this is a bad guys, but not for the conjecture. So this one comes from geometry. It has a Frobenius structure. The point is just you cannot reduce mod P, so you stay at the level of p-adic equation, but you cannot reduce mod P and get some information mod P for that one. So the method I'm going to present here today doesn't work, but just does not give any contradiction with all the whole picture. But this picture told you that we have something very general that should be true, and in this particular case of our sequence FR, look at this. If I put a P inside, what we have is not only a difference equation, but we have a difference equation of order 1. Okay? So for FR, it satisfies a differential equation of order R. Order 1 is better than order R. Not. And that's the point. That's what we want to use. Okay? For each, the point is that independently of R, we have order 1 Frobenius equation for all prime. Order 1 is really the easy case in difference or differential Galois theory. So So we want to use this order one, and this is exactly what we are going to do. So this is clearly the trick we want to use. And in general, if in this world picture, you get order D equation of, with respect to this Frobenius. It's expected that this D does not depend on P. So the conjecture would be that this D is uniform. So in general, we should consider this equation of order D. But up to now, we are only we have efficient tools. So we are trying to develop a kind of Galois theory, mod P, a general Galois theory, but it's still only starting. But what we already done is ready for order one. Okay. So all this, what is interesting is that there are plenty of examples where we get this order one equation. So now I'll give you a formal, more formal definition. Just maybe check time. So, as I said, the target we have are G-functions, so they are solutions of differential equation. But the result I'm going to present has nothing to do with differential equation. So this is something independent that happen to work for this kind of function. But in all the example I know comes from solution of differential equation and G-functions. But the proof is completely independent. So what we define, I'm going to define it in one variable case, but it's also work as well with no additional difficulty for power series in several variables. Okay, just to simplify. So we have the set L or S. So this is a set of power series I'm going to define. So here, R is an integral domain. So K is its field of fractions. S is a set of prime ideas in R. And we denote by if P is in S, we denote by RP the localization of R. Okay. Now we say that for Z, which belongs to K, so the field of fraction of Z, so a polar series like this, belongs to this ring LS if we have the following things. So first, S belongs to RP of Z for all P in S. So just saying that we will be able to reduce the coefficient modulo the prime in S. So the second thing is that the residue field, R T, is a finite field, and we assume that this characteristic is P. So that's why we call P for the prime ideas, and we assume that the residue field has characteristics small too. And then we want that f of Z is congruent to some AP P. So if I reduce mod P to some ZPK, okay, yes, 3, and this belongs to RP, so our finite field. It's a rational function.
So, a question. So the second condition, that does not depend on f, right?
No. No, but we assume that, so to define this, this set of power series, so they are defined by given a ring, an integral domain, and a set of ideals, of prime ideals. So then the member of this ring, of this, no, it's not a ring, but the member of this set, so are the power series that can be reduced for this, these ideals. And then, because here, you see, we use the Frobenius with P, we have to say what P is. We want to, that this P corresponds to the characteristic of the residue field, which has to be finite for all P in S. So all these things, so this is for all prime in S, and this is also for all prime in S. Okay? So we just mean that you have a Frobenius equation of order 1, maybe for an iteration of the Frobenius. But you have order 1 for either the Frobenius or an iteration of the Frobenius, which really looks like this. And the last condition is that the 8 of this AP, this is a rational power series. So the 8 is the maximum of the degree in the numerator and the denominator. We ask that this is at most C to the P to the K for some C that does not depend. Does not depend on P. So on P.
What is it?
So this is a rational power series, so it's a quotient of two polynomials. So the 8 is the maximum of the degree in of the numerator and the denominator.
Oh, okay.
It's a way to look at the complexity of this power series. And in our example, so this is purely abstract because we have an integral ring and so on. We put this condition, but we are clearly motivated by this kind of function. And each time you get this kind of equation, say for G-function that you reduce mod P, the last one is always satisfied. But we are not able to prove that it is satisfied in general, and this is really crucial for the proof. So we really need it, but in all examples where 3 is satisfied, 4 is also satisfied. So it's a conjecture that this is always satisfied. And then when we have this definition, so here, as you see, there is no differential equation at all. So the algebraic independence criterion we have, so with Bell and Delaygue, so it is this. So assume that S is zip. So zip is for zero intersection property. So it just means that the intersection of P for P in S for P intersection for no, P in S prime in S infinite is 0. So in the context we are interested in, K is a number field when we have a G function. So R is a ring of integers of this number field. The P are prime ideals, so the reduction is always a finite field. And just because the ring of integer of a number field is a Delaygue ring. The integration of infinitely many ideas is always 0. So this is always satisfied. It just means that we need S to be infinite when we are over a number field. Okay? So, but otherwise, if we want to be in a larger context, we need this. But this is always satisfied. So when we are in a number field, the question is just S has to be infinite. We need infinitely many prime ideas. Okay. And then.
So the condition is vacuous if S is finite?
If S is finite, I don't see an example where you can expect.
I mean, the condition would not be satisfied. I mean, the intersection would not make sense, so it would be vacuously satisfied.
So, I mean, I'm not sure to understand what you say. If S is finite,
Yeah, so
you cannot really expect.
You can't have an S prime, which is infinite. So
No.
So
No.
So it's vacuously satisfied then?
Yes, but this is not, okay. Okay, so, yes. Okay, so if I tell this like this, so it has to be infinite. Yeah, you're right. But anyway, if you only have finite ideas, I don't know any situation where it would be enough to know something just for a finite number of reduction and to come back. So we want kind of local global principle.
But you know, in an abstract situation,
Yeah.
it's just an integral domain.
Yes, I understand. But yeah.
I'm not acting your application.
Yes. You're right. If I write this like this, I should ask this, maybe. We'll check, but we can say infinite. It's not a big deal here. So the theorem that if F1, Fn are n function in this Rs, so just as things is, and algebraically dependent over A of Z, then there exists A1, An in Z, not all zeros, so that F1, A1, Fn, An, so its product is a rational function. So which, first of all, really look like Cauchy's theorem. So in a sense, you have order 1 equation, and you say, okay, if there is an algebraic dependence relation, it has to be of a very special type, right? And this is exactly what we are going to do. The only point is that you can reduce the situation mod P. Here you can prove a kind of Cauchy's theorem for this equation. But then you have to find a way to come back over Q, for instance, in this example. And this is exactly what we can do. And I briefly, basically explain why this is possible. And once you have this, just I want to mention, if we come back to this FR, that is very simple to prove that they are algebraically independent. So the FR, let's erase this. So each Fourier series FR belongs to L of Z, and I can choose for P, for S, the set of all prime numbers. So the coefficients are belongs to, well, they are in this, so they belong in particular to the fraction field, which are the rational numbers. If I pick a prime number, any prime number, z over pz is a finite field of characteristic p. This with k equal 1 is exactly this equation. And the height of the rational function here, in that case, is just a polynomial, and the degree is p minus 1. So here k is equal to 1, so I get this p minus 1, I can choose c equal 1. Okay, so this is satisfied. And now I can use the criterion, and so let us assume that F2 and 2Fr are algebraically dependent. Okay, because F1 is algebraic, so in the theorem it starts with 2. So assume that there is an algebraic relation for some R. Then I get something like this with coefficient A1, AR. So, and I choose R to be maximal. Maybe R is not a good choice. Yeah. S to be maximal such that AS is non-zero. So in this relation, I get something like this. Not all the AI are 0, so I choose the last one, which is non-zero. Okay. So what I get is there exists a rational function, rational polar series, such that Fs As, so it's equal to, I move the other one on the other side, so if it's A2 minus A2 Fs minus 1 minus As minus 1 times R of this. Okay? But now, this function Fs, the larger S is, smaller is the radius of convergence. Okay. So here the radius of convergence is z0 is 2 minus 2s. Should be s. Okay, so this is the radius of convergence of this function
What
fs.
does z0 mean here?
What?
What does z0 refer to?
To the radius of convergence of this series.
Radius convergence.
But the other here have a larger radius of convergence. So each fi is analytic around this z0. Because of the AI, they are meromorphic. And this one is meromorphic everywhere on the plane. So that the left-hand side is meromorphic. At z0. On the left-hand side, you can use this asymptotic of coefficients using Stirling formula to see that this is not a pole. The singularity cannot be a pole because it doesn't fit with the asymptotic of a pole. Okay, so you get the contradiction. And from this, you have all the F2 or 2Fr are algebraically independent for free, in a sense. Okay, so once you can use this. In many cases, you can then use. This is why I say 1 plus 2 will replace this 3, the differential Galois theory. So we use reduction of P, this criterion, and then easy stuff with asymptotic. Okay? Because now we have only one monomial, so asymptotic really can be used. Okay? So like this, we can prove many. In our paper, we give some family of examples where this works. And they are not always related to hypergeometric series, so I can just maybe cite one other example. So then we have example with infinite families like this, but also, for instance, if you consider the 4 function, so f of z is the sum of 4n factorial divided by 2n factorial n factorial square dn. G of z is the a priori one, the nk square n plus kk square. And then we can get some hypergeometric series like this, 1, 6, 4, 9, over 2/3 and factorial n. And the last one, so for instance, I pick this 4 series. We'll not explain exactly why we choose that one. It was 1. Over 7n. So here I've mixed between 4 series. 2 are hypergeometric. This is a priori series, sum of binomial, and this is quotient of factorial ratio. So the not completely belongs to the same families in general. So if you want to prove algebraic independence of those, again you have to mix the differential equation all together. Those hypergeometrics, you have good knowledge of the Galois group, but for a priori or that one, it's not completely clear. And when you put this all together, it seems that people don't know how to prove that it is algebraic independent or not. But you can use this criterion in the same fashion I just mentioned. Here you just see that these 2 series, they cannot be reduced mod p for all prime p because of this 3rd and 1, 6, and 7, and 5. So this one you can, for instance, we will get equation like this only for the prime that are congruent to 1 mod 35. So 35 from 7 times 5. And those one, it will work, so they satisfy this kind of equation only for the primes that are congruent to 1 mod 6. So at the end, when we want to mix these 4 together, the set S we choose is a set of primes that are such that P is congruent to 1 mod 210. And the point is that each time there are good primes, I mean, which offer such equations for hypergeometric series, we can choose primes that are congruent to 1 mod something. And by Dirichlet's theorem, we know that there are always infinitely many primes here, and if you combine both, we get again the prime congruent to 1 mod something other, and still we get infinitely many primes in that. So we can make this work and find the equation, and then use a bit of singularities and get the algebraic independence. Right? Just maybe I can, I don't know what time is it, more or less. Just to very briefly try to describe how we get this. Okay. And it's not hard, but I will just sketch the argument. A complete proof is not very long, but try to give you the idea of that. the point is that when p is fixed, so imagine you start with your function like this. Okay, here the k may change, may be different for the function, but you can use some iteration and choose a LCM or something to get the same k. Okay, and the condition here when you iterate, because the p is also moving, is still satisfied. So there is just a small thing to check, but the point is that you will get all the functions basically will satisfy the same equation, I mean with same k at different AP. So what you have mod p is a system of order 1 equation. Of course we are over a finite field or so, or we just don't know even we are over a finite field, so it's not complete, does not completely fit with a classical theory of difference equation. For instance, sometimes we need algebraic closed field or things like that. But really by hand, you can prove a Cauchy theorem, saying that if you have order 1 equation like this, so if you, so your function, where it is, so when you have your, if you have several function fi that satisfy an equation like ai sigma of fi, and just sigma is an endomorphism, injective endomorphism over any ring, I mean maybe integral ring. If you have something like this, you will prove that there exists some m1 to mn in Z, not all 0, such that if the Fi are algebraically independent, then the AI satisfy AI Mi, so A1 and 1 product up to An and N is equal to sigma of R over R. So where, so I should say that, so L is the field, sigma is an endomorphism, so M is a subfield, sigma is an endomorphism of L with sigma of n is included in M. So the Fi, they are in L. And here the I belong to M. And then the R here belongs to M too. Okay? And this is really like Cauchy for a difference equation. You just choose if they are algebraically dependent, you choose a relation with a minimal number of monomials, you apply the automorphism, you will find another one, you make a difference, find a shorter one, it has to be 0, you get this. Okay? So now we will be in the situation where we get something like this, but our AI, so there are those rational functions, so we are in such situation. And what you can prove is that if the algebraic relation here, algebraic relation of degree d, so you get, for instance, that each mi is smaller than d. Okay, so when you find your Cauchy expression, so depending on the bound of the algebraic relation, you can also have a bound on this mi. Okay, and we are going to use this because in our situation we start from assuming that our J functions, say, they are algebraically, these series are algebraically dependent. So there is a relation of degree D, but D, I mean, does not depend on the reduction mod P. Okay, so the D is fixed. Then we reduce mod P. Okay, and we are going to find an algebraic relation for our Fi mod P. Okay, but for the same degree D. And then we use that this Fi satisfies this kind of equation. So we get something like this with a bound that does not depend on P. Okay, and then roughly what we can say is that in this situation we will find that we have this AI P, so A1 P M1 to A and P and P is some rational function, so R of ZPK This is what the kind of situation we get. Because we have this finite field of characteristic P, and maybe if we have iterate enough, this R of ZPK, this is just R of ZPK, so we get something like this. Given rational function to pk minus 1. But now the point is that all the mi are bounded independently of P, and we have a bound of the AI. I mean the 8 of this rational function is at most P to the k. So this proves that, because here it's to the power P to the k, so the 8 of R is bounded independently of the prime P we are reducing. Okay? Because here this is something at most P to the k time constant, and these are constant, does not depend on P. So the whole thing is something in P to the k. And here we have a rational function to the P to the k minus 1. So this one has to be have a 8 bounded uniformly in P. So and once you have this, you just write I think very classical. So you just write you say H of Z is so you start with function F1 Fr. So you have F1 of Z minus M1 Fn of Z minus Mn, where the Mn are those guys. And the point is that because they are uniformly bounded, you get different guys for each reduction. But by pigeonhole principle, there are infinitely many primes such that all the mi are the same. So you can work with fixed mi by changing S by a subset S prime, but which is still infinite. And so if you get this H of Z, it satisfies H of ZPK over HZ is just this A1, this product, A1Z M1, A and Z, and N, and this is just R of Z to the PK minus 1. So roughly it means that again here H of the pk is F of z to the pk, so you get this pk minus 1. And so what you have is that this function h is just this rational function r. Okay. So this means that, but this is only true modulo some infinitely many prime ideals, all right? But the point is that because the order the 8 here is bounded independently of P, what you get is that something like H of Z, H of Z, Z square, H of Z, up to some Z to the M, H of Z, and 1 Z to the M. So for some M, natural number M, all these power series, so they are linearly dependent over Fp for all P in some infinite set S. And this you can lift because this is just some, you can write a determinant that is 0 for infinity many primes, so it is a 0, and then you get it. Okay, so really it's that, the point is that it was not clear, even if you have an information mode P, that you will be able to lift it to Q, and this is really because you have this condition that gives you this uniform bond here, and then you can lift the thing. And now the point is that this is not artificial, because in the sense that in all the examples where we get this is also satisfied. So it means that with G function we are in the natural situations, and each time you find this order 1 equation, so the general situation is that you have order, say, D equation, mod P. For some subfamily you have order 1 equation, and each time you have order 1 equation, this is also satisfied, and then you can apply the thing. Okay, so this is just a trick to prove algebraic independence by this reduction mod P. I'm going to stop here.
Do we have any more questions?
So here is a just idea. I don't know whether it works or not. So you've given this F1 up to Fm.
Yeah.
And they're all differential algebraic.
Yes.
So if you adjoin them onto a ground differential field, you have differential transcendent degree 0.
Yes.
I mean ordinary, let's say. Right?
Yeah.
And now with a primitive element, if you can compute it, I don't know, then it would be just generated by one single element. Now, if you can find out the let's say, the transcendent degree,
Yeah.
and if that turn out to be the sum of the transcendent degrees of each one of them, then they will be independent, otherwise
Yes.
they would not. Is that correct?
Why otherwise? I mean, the first part I'm okay, but when you say otherwise, they would
Well,
not be.
you see, if the F are algebraically independent,
Yeah.
then the transcendent degree will be the sum of each individual one added together. You know the order of the differential equation they satisfy, right?
Not necessarily. It's not always true. I'm not sure that I will understand.
So
you start with some for each Fi.
Yeah.
You
It's
look
satisfy the differential equation.
So you look at
You look at the
the
transcendent
vector
degree.
solution.
Right. You look at the, well, you could say, or let's just look at one of them,
Yeah.
all right? There is a transcendent degree, which is the order of the differential equation, no?
No, it's
No.
not always the order of the differential equation.
Because
It's just the dimension
Well,
of the
I
gamma
mean-
group.
Yeah, but if you choose a differential equation which is minimum order,
no,
No,
but
No?
if it's no,
you get only linear independence,
Right.
but not. That's the whole question, because algebraic independence it will give you in terms of the eventually in terms of the dimension of the differential gamma group.
right?
But this dimension is not always maximum, so that maybe the gamma group is not SLN or GLN.
Well, okay, but.
If it's much smaller,
Okay, but you do know the dimension, right? I mean, the dimension of the gamma group is the transcendent degree, is that correct?
yeah, the dimension of the but the dimension of the Galois group will be the
each one,
terms under
each one.
degree
Yeah.
of the.
No, not the degree, so not the order of the differential equation.
But the dimension of the Galois group
Is the transcendental degree of this field generated by
all the solution, fundamental matrix, all
It's
solution.
fundamental.
all the solutions.
Not only a single
Not
vector.
a single one, right, all the
Yeah.
solutions.
It's different.
It's a bit different.
Mhm.
So in some cases, everything is algebraic independent, and this is the generic case,
Mhm.
where in that case you say, okay, the Galois group is maximal, all things are algebraically independent,
Right.
and then it can work. But really the point is that so if you consider, say, hypergeometric series, so sometimes the Galois group is not SLN or GLN, it's smaller, and then you mix smaller things together, and you have to prove that these things are still independent. It can be really tricky.
But if you write down the fundamental system of solution,
Yeah.
are they algebraically independent?
Not
Not
necessarily.
necessarily.
The idea of differential
Sine and
Galois
cosine.
Oh, sine, cosine.
sine and cosine. Yeah.
Okay.
All the Galois theory is to try to describe this relation, possible relation. But if you pick
So
a differential equation at random, maybe you are in the case where there is no relation. But all the thing is that sometimes there are relations. And
you have to ask for you have to say this is a generic solutions then.
I mean,
That's for sure, because otherwise you choose zero.
right.
It's homogeneous.
so, for instance, sometimes
Well,
the G-functions, they form a ring, so there are plenty of relation between the elements. So you cannot expect that they are always algebraically independent. Just we try to buy tools for study the question.
So, here's a very stupid question, I guess, since I was stupid already. Shouldn't have been on this camera. So if F1 is sine and F2 is cosine, what would this thing tell you?
Nothing, because if f1 is sine,
It's a G function.
it's E function because of the factor.
Well, I mean, we know
We are
that,
not-
but I
we are
mean,
not
you go
in this
through
thing.
this whole thing, this whole machinery that you do.
You
what-
cannot use it
Huh? You cannot use it.
because it is based on this reduction mod P stuff.
Okay.
But actually, it's not completely true because one thing so this theorem we just published last year, but we proved it some years ago. And one thing we are going to do with Bell and Delaygue is to try to prove these similar things with E functions. But then you see the point. You cannot reduce mod P. But there are a trick for that, which are known for a long time, using so-called divided power structure. So this is something to make still some competition mod P, even if you have n factorial or power of n factorial at the denominator. This has been used in crystalline cohomology and things like that. So what we believe is that to have also something like a transfer principle. So when this work with some G function and we get algebraic independence, and you look at the same, we have some G function, we just prove they are algebraically independent. We look at the same E function, which are obtained just by dividing the coefficient by n factorial. Our hope is to prove that they also are algebraically independent. Okay, so to have this transfer principle, this is something which we're working on.
Can the three be, the signal that you're using is the Frobenius Z to Z to the P. Can you use other difference operator?
No, you could imagine.
Like a Q difference operator?
I mean, here you could imagine something purely formal where we just replace by a kind of order one equation. No. I'm going to say something wrong. I mean, here with the Frobenius, we have this simplification like
Yeah, you can move it in and
this
out.
r of z to the pk divided by r of z becomes something to the pk minus 1, and this is from what we get this uniform bond on R. So in that case, you have to say something more tricky. We have an operator with some additional conditions that will do essentially the same work. But the main point is that this situation really occurs in nature in some sense because it occurs with G-functions. I don't know a situation like this, a similar situation with other kind of operator. So I'm not aware of such examples. So really we start with, when we get this result, we start from this example of the series FR, the sum of the two nn to the R, the n. And once we get these examples, we try to figure out why it works, how it could be generalized, and then we really comes up with this definition. And I just write it down with an arbitrary ring and so on, because it's just fun to see that you don't need the differential equation. But my feeling is that if you are in a concrete situation where this happens, probably the function you start with is the G-functions.
You don't
Okay.
know that though.
I don't know, I'm not sure, but all interesting examples I need.
Any other questions? If not, let us thank you for